I don't know if waiting a minute is...
I don't know. Yeah.
That's still some people coming.
Yeah.
They were at breakfast, so they will show up eventually.
If we wait too long, then the end will get cut off of the recording.
I think it's plus minus 10 minutes.
It's not. I don't think it's 10.
Oh, that's what skip.
Okay,
Well, we can,
that's not the experience.
Yeah.
So why don't we get going? All right. Good morning, everyone. Welcome to the last day of TASI. I just eavesdropping. I've overheard a number of exciting events happened last night, so that's why probably it's a relatively thin audience. So I'm sure people will be dropping in, but we're delighted to have David giving his last lecture. So let's do it.
All right. Thank you for being here at 9:02 a.m. Your sacrifice is appreciated. All right. So in my lecture so far, I've told you about several ingredients that go into the conformal Bootstrap program. We can take 4-point functions of operators, expand them in conformal blocks, write down the crossing symmetry conditions, formulate some logic that allows us to try to prove contradictions from crossing symmetry combined with unitarity or positivity conditions. And this approach has led to a number of kind of really exciting bounds and results for interesting theories. So at the very end of last time, I started talking about one of those, which is the 3D Ising CFT. So I just wanted to start off by saying a little bit more about this theory and why it's important and what we know about it. Okay, so first of all, it shows up all over the place in the real world. So you look at the typical phase diagram. For a fluid. Of course, it has solid, liquid, and gas phases, but there's always some kind of point at the end of the line separating liquid and gas phase, and that's called a critical point. And in basically all fluids that we know about, the dynamics of the critical point are described by the critical 3D Ising CFT. So that's one place where it shows up. Another way it's often realized is through a lattice system of interacting spins. So you can write down some lattice Hamiltonian, which involves a sum over nearest neighbor interactions of some spins, which can either be spin up or spin down. In the continuum limit, this theory can be tuned to a critical point, and that's also described by the 3D Ising CFT. And then finally, there's a field theory way to describe it, which is the theory of a single interacting scalar field in 3 dimensions, which, in general, you might imagine has a kinetic term, a mass term, quartic interaction, and so on. This theory can be tuned. You tune basically the ratio of m squared over lambda so that the fluctuations are massless at the quantum level. And it also has a critical point described by the 3D Ising CFT. Yes? That might be too strong, but basically all of the common fluids that you might think about.
Critical point, not a triple point.
Yeah, not triple point. This is the triple point. This is the critical point. But
still a large number of examples.
Very large number of examples. Exactly. There are of course other phase transitions in real-world substances that are in different universality classes, right? So this is not the only thing that can happen, but the 3D Ising one is extremely common. Okay, so I just wanted to say this is kind of the notion of universality, right? There's lots of different kind of pictures of the UV physics that can be described by the same physics in the infrared. Now there's also been, there's a very long history of trying to understand this theory. For example, there's the Wilson-Fisher fixed point in 4 minus epsilon dimensions. That's basically phi to the 4th theory in 4 minus epsilon dimensions. You can find a critical point perturbatively in epsilon and calculate the properties of the CFT order by order in the epsilon expansion, right? So in that, in 4 minus epsilons, we have a scalar operator, sigma, which is, in this description, is kind of, roughly speaking, the phi field. And in 4 dimensions, a free scalar has scaling dimension 1, and it gets some correction, minus 1/2 epsilon, plus so on. If you extrapolate epsilon to 1, then you get 1/2, which is the scaling dimension of a free scalar in 3 dimensions, and it's a good starting point for thinking about this field. Then there's the second operator, epsilon. It's the first. Notice this theory has a Z2 symmetry under phi goes to minus phi, so the first operator is Z2 odd, the second operator is Z2 even. This is roughly phi squared. And that has scaling dimension 2 minus 2/3 epsilon plus ... And so this tells us we might expect, if I extrapolate epsilon to 1, we might expect it to be a bit bigger than 1, somewhere between 1 and 2. Okay, so I started telling you about some Bootstrap results. So one of them was looking at 4-point functions of a scalar sigma and placing an upper bound on the first scalar appearing in the sigma sigma OPE, which we're just we're defining that first scalar as epsilon. The OPE looks like identity plus epsilon plus ... So this is the definition of epsilon. It's whatever appears there. And if we make the gap until epsilon too big, we can find this linear functional that we talked about last time, which can rule out the existence of solutions to crossing symmetry. And we see a bound that looks like this. So let me label my axes. So here we're in 3 dimensions. A free scalar in 3 dimensions has dimension 1/2. So that sits right here. And the phi squared operator has dimension 1. That sits right here. So this corner is 1/2 1, which is where a free theory lives. This is an upper bound, so everything out here is excluded. And the first thing we know is that basically all 3D CFTs that are unitary or reflection positive need to live in this space somewhere. Yes?
From what you showed us last time, is it clear that this is supposed to be an upper bound on things?
Is it clear that it's an upper bound?
Yeah, from what you showed us last time?
Well, so what I showed you last time is a logic for making some assumption about the spectrum and then deciding whether you can prove a contradiction or not. So the statement is that if I make the gap too big, then you can start proving contradictions. And that's why this region is rigorously excluded.
I was wondering whether like it's easy to see that clearly very high delta, it's going to be a contradiction. That the bound is from above and not from below.
So is it easy to see?
Oh, well,
Yeah,
easy.
yeah. I think it's not completely trivial. You could have imagined there were some solutions that had no scalars and no scalar primaries, and all the scalar operators were somehow descendants. A priori, you might have imagined something like that could happen. Now, of course, you know that whatever bound you get can't rule out known solutions, known CFTs, or known solutions to crossing. So for example, there's a whole line of solutions that lives down here, where delta epsilon equals 2 delta sigma. This line of solutions is what you would call a generalized free theory, or a solution where the 4-point function of sigma factorizes into products of 2-point functions. And in this solution, the first scalar appearing in the sigma sigma OPE is like the sigma squared operator, has twice the dimension of sigma. So there's a whole line of solutions that we know exist. So you couldn't, you know, a priori you couldn't have ruled this out without making additional assumptions. Okay, so of course the other interesting feature of this bound is there's some kind of discontinuity in it. So this happens at like 0.518 on this axis, 1.41 on this axis. You can even see from up here that these are close to where you expect these operators to be for the Wilson-Fisher fixed point. And in fact, there are much more precise Monte Carlo simulations of the 3D Ising model that tell us this data to several digits, and you can see that this location of this kink basically nicely coincides with that known data. So that didn't have to happen. This is kind of an empirical observation, but one we've kind of been running with in the Bootstrap. And so, there's lots of questions you can ask. One question you can ask is whether you can somehow turn this observation into a real kind of predictive scheme. Okay, can I use Bootstrap to compute the scaling dimensions or critical exponents of the 3D Ising model, kind of rigorously? In particular, here we can locate the kink, but it's not very rigorous. There's no rigorous statement. You could ask, could you place like both upper and lower bounds on these scaling dimensions? And that's something that you can't do very easily with this single correlator, but you can do with multiple 4-point functions. So to kind of push this farther, one thing you can do is, instead of just 4-point functions of sigma, you can start looking at mixed correlators. For example, combine all 4-point functions containing both sigmas and epsilons. Notice I'm making use of the Z2 symmetry here. Sigma's odd under Z2, so I only have an even number of sigmas that I've put in these correlation functions. Now, okay, one immediate objection you might make is that last time we started expanding 4-point functions of identical operators, we saw that coefficients in that expansion were positive because they were squares of 3-point coefficients. And that was important for the logic of trying to rule things out. Here, you take this kind of mixed correlator, you expand it in these OPEs. Suddenly, I start getting things, products of different OPE coefficients that are not obviously positive. And so that's the first issue you have to contend with. It's actually not hard to do. You basically have to not just have positive coefficients, but take advantages of some kind of matrix positivity. And in particular, kind of the crossing relations for this system can be organized into a kind of matrix form. Okay, let me write it like this. Okay, so what I'm doing is, first of all, separating my operators into Z2 even operators, O+, and Z2 odd operators, O-. Z2 odd operators show up if I take, it's like a sigma epsilon OPE. And then for the Z2 even operators, as I just explained, they can kind of show up in the sigma sigma OPE or the epsilon epsilon OPE. But you can reorganize the contributions into a form like this, where I have a vector, kind of a 2-vector of OPE coefficients for each operator, and some 2x2 matrices sitting in between them. And here this I labels the different crossing equations that I can have. Okay, there's one crossing equation for this correlator, one for this correlator, a few for this correlator, and so on. So if I can write my crossing equation in this way, then what I can do is I can apply some functional alpha here and here, and demand that the action of this functional gives me a positive definite 2x2 matrix. Okay, and if I have a positive definite 2x2 matrix, then when it's sandwiched between this vector of OPE coefficients, I'm still guaranteed to have something positive. Okay, so that's kind of how you generalize the logic. Yes.
So you used set 2 to say that you would write down these correlators, but does that tell Bootstrap also that actually the advantage there are ones with odd numbers sigmas?
Sorry, say it one more time.
So you said like set 2, I only need to write down these 3 correlators, but does that also tell the Bootstrap that the other ones actually vanish?
Oh yeah. Yeah, that's right. So for example, the sigma epsilon 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 correlator vanishes.
Yeah, it does, but does Bootstrap know that if I make Bootstrap with 3 to the right, the left, sorry?
Does Bootstrap know that? Well, it's all so all those kind of Z2 symmetry selection rules get implemented at the level of 3-point functions, like which operators can appear in which OPEs, which 3-point functions vanish, and so on. So I don't think you'll get any new information by saying this correlator vanishes, because it's basically already implemented at the level of the 3-point functions in this equation.
Conformal blocks or something? Because I mean, they only had like delta L indices, right? They didn't have like a set 2 in the sticky index also.
So the conformal, yeah, when you have different operators here, then the conformal blocks, you need a more general form of the conformal blocks than what I wrote down, which depends. They start depending on the differences between the external dimensions. So I didn't write down that formula for you, but yeah.
What exactly does O run over again?
This O runs over all primary operators in the CFT. And in particular, here I've divided those into Z2 even operators, O plus, and Z2 odd operators, O minus. Now, of course, there are the kind of additional selection rules that we've described, like only even spin operators show up in the scalar-scalar OPE between identical scalars. So that's also incorporated here.
So do we have to start off by saying we have some list of primary operators besides the sigma and epsilon?
So we don't need to make a list. So right now we're allowing any, some arbitrary spectrum of operators to show up to these selection rules that we're imposing, like even spins, and so on. So in the way the logic is formulated, we impose this positivity. We say this has to be positive, and we want it to be positive for any possible operator that could appear.
So totally independent of what delta or L might be for these other operators, we want this to be positive, and that can be imposed. We don't need to actually know what.
Correct. Correct. Yeah. So that can be imposed. Basically, this positivity condition can be rephrased as positivity of some polynomial in delta, and a polynomial which is positive from 0 to infinity. That condition can be re-encoded by a statement that this polynomial is a sum of squares plus x times another sum of squares. So there's basically a theorem you can use to rewrite this polynomial that's positive over a whole continuous range in terms of sums of squares, and that gets rephrased in this language of semi-definite programming. So yeah, so in the way the logic is formulated, you basically impose positivity on a continuous range of deltas. You're allowing anything to appear, and you're not making any assumptions about the spectrum. And you can still derive these bounds, basically making no assumptions. Okay. Good. Other questions?
Can we also think about this as like a all-in-one, as like 2x2 block diagonal matrix, kind of encoding the sum?
Just grouping these together.
No, for just in the, say the first sum, like we have a 2x2 for each O plus in the sum. Do you like think about those separately, or?
Yeah. There's a for each O plus there's some 2x2 matrix here. That's right. Yeah. Because these O pluses have, this matrix contains the conformal blocks. Each O plus has, say, a different spin, right? So you need the conformal blocks for that spin in that 2x2 matrix, and so on. Yeah.
At some point, you just have to evaluate it at some points, right?
At some point, you have to do something to turn it into a finite number of constraints. And evaluating at different points is one option. Taking derivatives and evaluating at a single point is another option. And that's what's done in practice. You expand this equation around the crossing symmetric configuration and take some finite number of derivatives. Good. Okay, so so if you do this, I'll make a similar plot. Well, so if you look at this mixed system and make no further assumptions about the spectrum or the dimensions, then you'll get a plot that looks basically the same as this one. You don't get anything new if you make no assumptions. Okay, so let me see, get some. So if there's no assumptions, you still get a similar bound. On the other hand, if you start assuming that these operators sigma and epsilon are kind of isolated in the spectrum from the rest of their operator cousins, then you start carving out more interesting regions. And so, for example, if you assume that the second Z2 odd operator, sigma prime, is irrelevant, and the second Z2 even operator is irrelevant. So now I kind of have a picture where I have the identity operator, I have epsilon, and then there's a gap until epsilon prime, and similarly for sigma. If I make these assumptions, then what happens is that this upper bound actually turns into some closed region like this. And it's kind of ends up being disconnected from something else over here.
You're assuming greater than or equal to?
It doesn't really matter.
Because you said irrelevant.
I said irrelevant. Strictly speaking, we kind of allow them to appear at 3, so irrelevant or marginal, but it doesn't really matter. Okay, so now I've made these stronger assumptions, and then we get this region. So now everything out here is kind of rigorously disallowed by the Bootstrap. We can find some functional that approves a contradiction, and everything in here. Everything in this little island and in this bigger region is allowed. Sorry?
How big is the island?
How big is the island? Yeah. So this kind of depends. So as I mentioned, we're basically, you can add more and more constraints. So we Taylor expand this equation around the crossing symmetric point. We can take more and more derivatives. This is like increasing the search space for this functional alpha. And as you do that, the island gets smaller and smaller. Okay, so the farther you increase the search space for a functional that can rule out these solutions, the smaller this island can get. So in this system, you can push this pretty far. So the island that's been computed from this system delta sigma, you can kind of determine it to 6 digits. Delta epsilon, 1.4126255, 5 digits. So this is kind of the level of precision. So you can make it pretty small, and this is the level of precision that you can get by pushing these numerics pretty far and trying to shrink this island as much as possible. Yeah.
So could you explain again how these constraints go into the Bootstrap equation and how that constrains the parameter space? I think I'm still missing something.
Yeah. Let me just go over here. So, okay, so we're looking for some linear combination of derivatives that has nice positivity properties when acting on these differences of conformal blocks. And so in particular, we want this to be positive. We want this in general to be some positive definite matrix. And then on top of that, we can separate out the known contributions, like the identity operator contribution. And we can normalize our functional on the identity operator, so it's equal to 1 on the identity. And then we get an equation that's like, if we can find a functional with these positivity properties, we get 0 equals 1 plus sum over positive things, and that's a contradiction. Right, so that's the logic. It's like everywhere in this region, we're able to find an alpha that implies a contradiction. Okay, was there another question?
So are you running against like that you don't have more compute time, or is that like the fundamental reason why you cannot make the
Good. So of course, we run this until computing time gets too expensive and it's difficult. I think there is a fundamental reason why, at some point, you push this correlator system far and it's not shrinking to a point. It's still shrinking to some finite region. And it's basically because, there are some operators that this system is very good at reconstructing in the solutions to crossing symmetry, and there are other operators that it's not good at reconstructing. And so, you could ask, what do you need to do to push this further? And one answer to that is going to a bigger mixed correlator system. And so I'll talk about an example of that in a moment. Yes?
Just to get some publicity, experiment is 2 or 3 digits on these deltas.
Yeah.
And Monte Carlo is, I think, between 1 and 2 orders of magnitude wider than what the Bootstrap gives.
That's right. And
Can you repeat that, or is the idea?
sorry, yeah, so just the idea is, I mentioned there were, experimental realizations of 3D-izing. Those can typically measure the scaling dimensions or critical exponents to 2 to 3 digits. Monte Carlo simulations do better than that. The most precise ones, kind of push this to, now I'd have to double check, but at least five digits, I think, maybe is the most precise.
So Bootstrap is winning.
So Bootstrap is winning. Bootstrap is more precise. And as I'll mention in a little bit, actually the most precise Bootstrap computations are more precise than this one. Okay, yeah.
You might be the first person to write error bars in this capacity. I'm sort of wondering,
Yeah.
if you're doing Bootstrap and you're getting rigorous bounds,
Yeah.
are those statistical error bars or are they rigorous bounds?
Modulo tiny errors from like the approximation of the conformal blocks and so on that are well under control, these are rigorous error bars. In the sense that, we're mapping out this region, points out here are rigorously excluded, right? So, you could ask how precisely do you map out this region? There's some algorithm for like reconstructing this shape, but we can, map it out precisely enough that we can claim these are rigorous error bars. Yeah.
Are there similar islands for epsilon prime and sigma prime, or looks at the plane of epsilon prime and sigma prime, or like of the following non-trivial primaries?
Yeah. So the question is, are there similar islands for other operators in the theory? And the answer is yes. So okay, so there's 2 things to say. So one is that there's kind of a non-rigorous method for reconstructing the whole spectrum. This is sometimes called the extremal functional method. And the idea is that if you go to a boundary of the space allowed by crossing symmetry, you can, I'll go over here. You go to a boundary, and then you start plotting the action of the functional on your crossing vectors as a function of delta. And basically, you've imposed that this is positive over a whole range of deltas. And what you see is that on the boundary, it has this very nice structure where it has a discrete set of zeros. And the locations of those zeros actually tell you about a solution to the crossing equation that you've imposed. So by looking at these extremal functionals, you can actually read off a whole spectrum. Now, it's kind of, it's non-rigorous. It's hard to, you have to do some work if you're going to try to assign error bars to these numbers. But you can learn a lot of data about the subleading operators this way. You can also try to formulate a logic that gives you rigorous bounds on subleading dimensions. To do that, you need to kind of isolate them, so impose some gap above them, and then you can try to get rigorous upper and lower bounds. So both of these approaches have been done. Yeah.
How do these results compare to like this fuzzy sphere regularization?
Mm-hmm.
Is that like more accurate or less accurate?
Fuzzy sphere is less accurate. Yeah, at least in the computations I've seen so far, fuzzy sphere tries to compute delta sigma and delta epsilon. The error is around the 3rd to 4th digit. The fuzzy sphere has other advantages, like they can more easily reconstruct some data that's a little harder to access with the Bootstrap. But in terms of how precise the results are, this beats it out. Okay, so let me just mention one more thing here. So let me give you some intuition for why these gap assumptions kind of give you an island. It's not rigorous, but you can, kind of think about what these are doing is they're ruling out nearby solutions to crossing symmetry that have low dimension operators in these sectors. And in particular, in the Wilson-Fisher fixed point description, in terms of a scalar field with a phi to the 4th interaction and so on, there's some equation of motion which looks like phi cubed gets related to del squared phi. Okay, this is the equation of motion of scalar phi to the 4th theory. Well, this is telling you that the phi cubed operator is not a conformal primary. It's a descendant. It's a derivative of something else, right? And so since we're classifying things in terms of primary operators, this is a Z2 odd operator. What this is telling us is that there's going to be a big gap in the spectrum of Z2 odd operators. Because after phi, the next one naively would be phi cubed, but it's a descendant. So then you have to go to phi to the 5th in order to start seeing the next Z2 odd operator. And so in some moral sense, imposing these gaps is like imposing that there's some equation of motion that this phi cubed operator, which naively should be there, is removed from the spectrum. You can kind of also see this. For example, you can like follow the bound, or follow, in this you could follow the boundary of the island and see what's happening. And so let me see, if I try to plot like delta sigma versus delta sigma prime, where I let delta epsilon follow the boundary, you can ask what happens. You can place an upper bound on delta sigma prime following the boundary using similar logic. And okay, so here's the Ising point. What you see is that you get some bound which is kind of low over here, and then as you approach this point, it spikes up and then comes back down. So this is, let me put some numbers on here. So this is like 3, where it would be marginal. And this goes up to around 5.3 or so. So you can kind of see it, in the space allowed by crossing symmetry that, at this unique value of delta sigma, is where you're allowed to decouple this operator. So that's kind of an important part of the structure of what's happening here. Yeah.
So for this the diagram is an island. This is like by imposing the gap here. But then when you describe this kink, you also said something like you have some make the gap large. Where does that happen?
Sorry. So there are different gaps. There are different gaps here. So over here, when I was talking about a gap, I was talking about delta epsilon. So that's the gap until the first scalar operator.
So that's the epsilon you read there.
That's the epsilon, yeah.
So but the epsilon on the first board, are they different?
The,
1 minus a half epsilon?
yes.
That's a difference of
Yes, sorry. Yes, I apologize. So this is in 4 minus epsilon dimensions, where you do these epsilon expansion computations. This is a different epsilon than epsilon operator of the theory. So I apologize for that.
Why don't you make those two epsilons in expansion as curly epsilon?
Wonderful idea. Let's try to do that.
Because you never write that again.
Absolutely. So this is going to be curly epsilon, and this will be non-curly epsilon. Thanks for the notational suggestion. Okay, good. So, oh, and yeah, just to mention this sigma prime operator. By the way, you can also like estimate it using the epsilon expansion, the curly epsilon expansion, and where you kind of think of it as the phi to the 5th operator. And it has scaling dimension 5. That's the starting point in d equals 4. Plus 5/6 epsilon plus corrections. So, so it all looks pretty consistent. The epsilon expansion says it's a little bit bigger than 5, maybe between 5 and 6, and the bootstrap bound puts it around 5.3. And actually, there, as I mentioned, there are kind of rigorous bounds on these from the bootstrap. So you can also there's a result that is 5.290611 with some error bars, right? Okay, so this is one success story of this bootstrap approach. You could ask, how would you make this more precise? How would you determine other CFT data? There's also like OPE coefficients you can reconstruct here and so on. But there's some data that you're not accessing through this system. One example is we've been talking about stress tensor 3-point functions. That gives interesting CFT data that's not accessed anywhere in this particular bootstrap system. So you have to go to a bigger system of correlators to start accessing this data. And so that's been one direction that we've been pushing on. Another question you could ask is, for what other theories could you kind of compute these small islands? And by now there's kind of a nice list of theories where we've been able to do so. So some other examples. Oops. In 3 dimensions are the ON vector models for different values of n. These are like n scalar fields. With an ON invariant interaction. These have the nice advantage that there's also, in addition to the epsilon expansion, there's also a large n expansion for these models. So for example, In 3 dimensions, delta phi is 1/2 plus some 1 over n correction plus dot, dot, dot. Now, if you start looking at things like phi squared in these models, there are different options, right? So there's like a singlet, phi I. There's also a symmetric tensor, Tij, phi j, traceless symmetric tensor, and so on, right? So there are different. Once you have a global symmetry, like an ON symmetry, you can divide your operators up into different representations of that symmetry. And you can separate out all these different contributions in the Bootstrap. So in particular, you can compute bounds like the scaling dimension of phi versus the scaling dimension of the leading singlet, ON singlet, in the Bootstrap for different values of n. Okay, where I've imposed that there's an ON global symmetry by saying I have 4-point functions of this ON vector. I can decompose it into different tensor structures of the ON global symmetry. There's a different crossing equation for each tensor structure, and so on. Well, what happens here? Well, first of all, what you get is kind of some family of bounds for different n's, and each one has a kink in it. These at large n, these approach 2 1/2, which is what the large n expansion tells you should happen at large n. On top of that, you can go to a mixed correlator system and impose some gap assumptions like we did over here. In particular, it's very useful to impose that the second ON vector, delta phi prime, is irrelevant. This is kind of the analogous condition motivated by the equation of motion, like we discussed up here. And that can turn these kinks into some islands for different values of n. Yeah?
Is that delta phi or phi prime on the x-axis?
This was delta phi I, sorry. Yeah, delta phi. Let's write it as delta phi. Okay, so here, this is some whole family of islands. N equals 1, n equals 2, n equals 3, n equals 4, and so on. And the locations of these islands or the locations of these kinks kind of match nicely to the predictions from the large n expansion once you get to sufficiently large n. Around n equals 8 or 10 or so, they start matching very nicely. At smaller n, the large n curve kind of goes down this way and misses the islands. Okay, so that's kind of, there's this whole family of theories where we can repeat these successes. There's another example, which are models of interacting fermions called Grosnovo-Yukawa models. We've also gotten kind of similar islands there. There's also been a lot of success at applying the Bootstrap to supersymmetric theories. So 3-dimensional ABJM theory is another example where there are very nice Bootstrap results that have some islands, and people can do precise computations. Okay, so what I want to tell you about next, here I focused on kind of the story starting from 4-point functions of scalar operators. Now I want to shift gears slightly and look at 4-point functions of the stress tensor. So in the first couple lectures, I gave you a formalism for talking about these, right? We can use embedding space, write down all the tensor structures. For each 4-point tensor structure that you could write down in the embedding space, you get some function of cross ratios. For each one of those, there's some crossing symmetry constraints. And that can all be imposed in the Bootstrap. So let me start with the stress tensor 4-point Bootstrap in 3D, where this has all been done, worked out very explicitly. Okay, so first of all, let me just remind you. So if I take the OPE of two stress tensors, what do I get? Well, there's still an infinite number of conformal primaries. You have the identity operator. We have the first parity even scalar, which I'll call epsilon here, with some OPE coefficient. And if you recall, when we looked at TT scalar 3-point functions, there was a unique coefficient. There's just one. Okay, so there's one structure. Now there's also the stress tensor itself that appears. Here, as you've seen in both my lectures and Tom's lectures, there are multiple structures. So we have this NB, this NF, structures corresponding to the free boson TTT 3-point function and the free fermion one. Here we're in 3 dimensions. There's no kind of gauge field structure, but there is, in general, a parity violating structure. Here I'm going to assume that my theory has a parity symmetry so that that's absent. Okay, so there's two coefficients. There's also a Ward identity that tells you that the sum of these 2 coefficients is related to the central charge of the theory, where the CT is defined as the coefficient in the TT 2-point function. Okay, so that's the structure there. And then there's other operators that can appear.
CT, the coefficient of the identity in that OP?
So you have a choice of normalization to make. You can normalize this so CT shows up here, or I could canonically normalize the stress tensor so CT shows up in all of the 3-point functions. You just have to make one choice and do it consistently. So I think, yeah, here.
If you write the 2-point function of TT, CT.
That's correct. So if I were in this normalization, then CT would appear here, absolutely. Good. Then, okay, so there's an infinite number of operators that can contribute, but the other one I wanted to bring your attention to is that in addition to parity even scalars, you could have parity odd scalars. T itself is even. And the point is that if I have 3-point functions between 2 t's and a parity odd operator, it can be non-vanishing because there is a parity odd structure that I can write down. So on the right-hand side, I'm writing down this structure involving an epsilon tensor. And so if I do a parity transformation, this side is odd and this side is odd.
But why did that? No, okay,
Yep. So yeah, so this is an important point. We're in a theory with parity symmetry. That means we can decompose operators into parity even and parity odd, and you can still have parity odd operators showing up in even OPEs as long as there's a structure that could accommodate it, a 3-point structure. Okay. Okay. Now. Okay. Now, how many crossing relations do I have to worry about when I'm doing this? Well, this requires some analysis because, kind of naively, you write down 4-point functions of spin 2 operators, and you'll see something like 625 different tensor structures that you can write down. Okay, so that looks scary. But then you start imposing various constraints. So there's kind of 625 conformally invariant structures. Now you impose parity symmetry. That cuts it down. To 313. You impose kind of permutation invariance. It cuts it down to 97. And then you impose conservation of the stress tensor. So that's really what's doing all the heavy lifting here. You write down the conditions where dt t equals 0 in the 4-point function. That gives you some differential equation relating these different functions to each other. Okay? You analyze those differential equations, and you see that actually not all these functions are independent from each other. If I know some smaller number of them, then I can reconstruct the rest by solving this differential equation. And if you do that analysis carefully, you see that conservation actually reduces things to, well, almost to 5 functions.
This seems like a way of generating prime numbers.
Interesting observation. Let's write a paper about it.
So in odd-space dimension, are also allowed to impose tracelessness or something?
Tracelessness.
Yeah, like if you trace one of the t's.
Oh, of course. Yeah, these t's are traceless symmetric tensors from the beginning.
Oh, okay. Right. But should it also be like that in even dimensions? Should it be able to reconstruct the vinyl anomaly?
In even dimensions, the stress tensor is also a traceless symmetric tensor in a CFT. So you can define a stress tensor that's traceless on flat space. On other curved manifolds, it might get a trace.
Right. But I'm computing that perturbatively by TTT correlators.
Uh-huh.
So shouldn't TTT, free T, shouldn't that be sensitive to the ANC coefficients or whatever?
Yeah. In 4 dimensions, you can write the TTT 3-point functions in terms of the ANC anomalies.
Yeah.
That's true.
But still they vanish no matter which one of the trace.
Correct. It's still traceless. In flat space. Was there another question? Yes.
Sorry, I'm still a little bit confused even from a previous lecture about how the counting on the constraints works for the conservation condition.
Yeah.
I guess for the 2-point function, I remember you get you lower it by 2 because you can apply it to 2 points, but then the 3-point function it grows, and now here it grows by a lot.
No. So here we're doing something different. Here we're applying conservation to the 4-point function.
Yeah, for each individual. So
Yeah.
I'm still counting 4 constraints, 4 equations that I can write down.
Yeah, it depends on the order in which you do things. So, we're also imposing that this is a permutation symmetric object under exchanging all the different t's with each other. And so if I impose conservation on one of them on a permutation symmetric object, it's not going to give me a new constraint. So anyway, so the point is we're putting all these things together, permutation, symmetry, and conservation, which is equivalent to doing conservation at each of the 4 points. Okay, so the claim is that there are basically 5 independent crossing equations that you get, plus some boundary conditions. So I said you get some differential equations from conservation, and we want to use these differential equations to reconstruct, all these 625 structures from the 5 that we're specifying. To do that, you need some boundary conditions. So there is also some constraints, for example, on the u equals v line, and some constraints at the crossing symmetric configuration itself. And so these are like boundary conditions on the differential equation that let you solve it. And in practice, it means you have 5 2-variable crossing equations, 9 1-variable crossing equation, and 8 point-like crossing equations that actually go into the final numerical setup. Okay, obviously I didn't derive these numbers for you, but it really requires kind of writing down this differential equation and studying its structure. All right, so what do you get? Let me draw you one of my favorite plots. Other lecturers had their favorite plots. This is one of mine. Okay, so I'm going to draw the scaling dimension of the parity even scalar versus the scaling dimension of the parity odd scalar, appearing in TT OPE. And if you make either of these too big, then you can find a contradiction and rule things out. And what does this plot look like? It looks something like that. And so let me start labeling some axes. So here is 1. Up here is 11. This is 7. This is 6. Okay, and then down here, maybe I have like 1 and 2. Okay, so this is, everything out here is disallowed. So this is the space allowed in these gaps by the stress tensor Bootstrap. And we could actually identify lots of theories living in this space. Every 3D CFT with parity symmetry needs to live in this region somewhere. And so, for example, there's a theory living up here. Anyone know what this theory is at 111? Yeah, I know, Matt, I know you know what the theory is. This is the free scalar. Why does the free scalar live up here? Well, so in 3D, phi itself has scaling dimension 1/2. The phi squared operator has scaling dimension 1. That's the first parity even scalar at 1. Now, if you want to build a parity odd scalar, a parity odd operator in the free scalar theory, it's actually quite hard to do. You have to write down something with an epsilon tensor contracted with various derivatives. You need multiple phi's to make it non-vanishing. And it turns out that the first such operator that's not a derivative of something else that you can write down has dimension 11 in just a free scalar theory. Okay. Now on the other corner, we can go down here at, let's see.
That's not right on the line. That's a little bit below the line.
So, so these are bounds that get stronger as you increase the derivative order. And so, as you increase it, this bound gets stronger and stronger. And I would say it's basically approaching this point. It's consistent with approaching this point. That's right. Okay. There's another theory way over in this side. It's 6 and 2. So this is actually a free Majorana fermion in 3D. Okay, so if I have a free fermion in 3D, its scaling dimension is 1. If you like the psi bar psi operator has scaling dimension 2. And if you look at how it transforms under parity, this is parity odd. Okay, so this is why a fermionic theory has a low dimension parity odd scalar. And now if you want to construct a parity even scalar, you have to kind of square it or do something else. Now, naively, you would want to just write down this operator, which has dimension 4. That's there in the theory of a free Dirac fermion, so I can go over here at 4. If I have a Majorana fermion, which is a real 2-component spinner, this just vanishes automatically because there aren't enough Grassmann components. So you have to add some derivatives in order to make it non-vanishing. Okay, so free Dirac lives here, free Majorana lives here. Now, this plot has this nice sharp drop-off. You can ask where that happens, and that's actually at 1.412, which you'll notice coincides with the scaling dimension of epsilon in the Ising model. So even in the stress tensor bootstrap, it seems to know something about the 3D Ising CFD. There's this sharp cliff at that dimension. And a reasonable conjecture is that the Ising model lives up in this corner. Actually, I would say prior to computing these bounds, basically nothing was known about the leading parity odd scalar in the 3D Ising CFD. Okay, so you see a lot. You can find other models in this space, like the ON models in the large N limit go to this point. There are like these fermionic theories live kind of down here. These Grosnovo-Yukawa models live down here. This corner is at 6 and 7. This is like a factorized 4-point function. If TTTT looks like products of TT 2-point functions, you might say this is dual to a free graviton gas in ADS with no interactions. So we'll call it free graviton. So the point is that you have some composite operators, like a TT double trace operator. That's a scalar that has dimension 6. And that corresponds to this 6. And then there's another operator you can write down involving an epsilon tensor, something like some operator like this, which is parity odd and has dimension 7, and that corresponds to this 7. Yeah.
I maybe just getting confused. For the icing showing up there, like close to 11 for
Yeah.
delta odd,
Yeah.
why doesn't that delta phi prime equals 5.29 show up there? Does that just not have...
Good. So we need to distinguish between the Z2 symmetry and the parity symmetry. Okay, there's a Z2, the Ising model has a Z2 global symmetry and a parity space-time symmetry.
That's the Z2.
Yeah.
Is
Yeah.
there some conjecture of what kind of theories are expected on the edge versus, is there like something special with things that appear on the edge versus the bulk or something? It seems like a lot of interesting things are at the edge.
A lot of interesting things are at the edge, but also some things are in the interior. All the theories at the edge are kind of extreme in some way. But
The free Dirac theory is two free Majorana theories, I guess. So it's not, it's
Yeah.
reducible in some sense.
in some sense, yeah, it kind of factorizes. That's true. Yeah, of course, there's other theories, like the theory of two free scalars that live in this space. Yeah, I don't. There's no sharp conjecture along the lines of what you wanted, but clearly these theories are special in that they're extreme in some way.
Could you just say again what GMY was?
Yeah, sorry, I didn't define these theories. Gross Nouveau Yukawa. So these are theories of say a scalar interacting with n fermions through some Yukawa coupling. And there's a whole zoo of these kinds of theories, but the simplest one has an ON symmetry rotating the fermions into each other, and that has a 1/n expansion, and so the large N limit of these theories is what lives here, and different N's kind of move in this space in some way. Okay, so this is the picture you get from the stress tensor Bootstrap. In my last minute, let me tell you what happens when you combine these systems together. You look at mixed scalars and stress tensors together. Okay, so this is kind of the state. The state of the art of the Bootstrap. Look at combining sigma, epsilon, and T mu together. So far, specifically targeting the Ising model, but you can really, you can look at these kinds of mixed systems in any theory. What do I want to say? So this system has roughly 30 crossing equations instead of 5. It's bigger. There's various OPE coefficients that are introduced in this system that we can constrain using the Bootstrap. Ultimately, there's like it kind of requires doing a search in a kind of 6-dimensional parameter space. So let me just tell you what those parameters are. So there's the scaling dimensions, but then there's also various OPE coefficients. And kind of the positivity properties of the Bootstrap are only sensitive to like ratios of OPE coefficients. So we can kind of normalize by one of our choosing. Okay, so these are all the coefficients involving these three external operators. And to really kind of get the most powerful Bootstrap, you need to search through this 6-dimensional parameter space to find the allowed region. There are various strategies for doing that, which I can tell you about after the lecture. Roughly, it corresponds to doing a search through scaling dimension space, which we call a Delaunay triangulation search, combined with a strategy for ruling out or finding allowed points in the space of OPE coefficients. This is called a cutting surface algorithm. But the point is that when you combine, but you can find allowed points in this 6-dimensional space, in this big Bootstrap system, and map it out. And so let me just give you a sense of what the end result is, since I'm basically out of time. Okay, so here's kind of the latest that you get for the scaling dimensions. And we also get very precise data for these OPE coefficients. In particular, let me just highlight, for example, these coefficients in the stress tensor 3-point function, we now know extremely precisely. So I'll just write those ones down. Okay, so now this is an extremely precise computational tool. We can answer questions like, how fermionic is the critical 3D Ising model? How much of this fermionic structure is there? This gives us a quantitative answer. This data also allows us to do things like compute energy correlators in the 3D Ising model that you heard about in some of the other lectures. And really, it's kind of the starting point for doing a lot of analyses. You could perturb away from the Ising model in different ways, do conformal perturbation theory. You can compute different observables involving energy flow. And you can get insights into kind of the deeper structure of trajectories of these models. So the future of the Bootstrap right now, at least part of it, is we've seen that there's a real benefit to combining these systems of correlators with spinning operators, like the stress tensor. And so far, it's only been done in this one context. But we have all these other islands in 3D, ON models, GNY models. Clearly, we're going to gain a lot by combining those with stress tensors and currents. There's lots of other interesting targets for the Bootstrap too, like conformal gauge theories, which haven't yet been isolated into small islands. But the hope is really that by looking at these bigger Bootstrap systems involving currents, stress tensors, and other operators, that will give us the right tools that we need in order to isolate kind of all of the CFTs that live in this landscape. So with that, I will stop, and thank you for your time.
We have our break. I just want to acknowledge David again. This was his last lecture. He's also one of our scientific organizers, planning the whole program, helped make TASI what it was. Let's give him a nice big round of applause.